Look up at the night sky on the clearest, darkest night possible, far away from the blinding glare of city lights. It feels as though you are peering straight into infinity. Thousands of glittering pinpricks of light stretch across the deep black canvas, creating the illusion that the entire cosmos is laid bare before your eyes. But that vast expanse is a profound cosmic illusion. In reality, your eyes are barely scratching the surface of what exists out there. You are standing on a tiny speck of dust, trapped inside a bubble defined not by the edges of physical space, but by the fundamental laws of physics themselves. Because light travels at a finite speed of roughly 186,000 miles per second, looking out into space is inevitably looking back in time. When you gaze at distant stars, you do not see them as they are right now. You see them as they were when that light first began its journey. This simple reality introduces a strict cosmic boundary. The universe has a finite age, which means there is a limit to how far light could have travelled since the beginning of time. Beyond that boundary lies an unseen realm, regions of space whose information has simply not had enough time to reach us. What we often casually call the entire cosmos is merely our own personal observable bubble. How much of this vast tapestry have we truly mapped, captured, and understood? Today, we will explore how much of the universe we have actually observed, how we managed to do it, and what remains forever hidden in the shadows. To truly grasp the scale of what we can see, we first have to dismantle our everyday understanding of distance and time. In our day-to-day lives, we treat space and time as completely separate entities. A mile is a measure of physical ground beneath your feet, while an hour is a duration measured by the ticking of a clock. But on a cosmological scale, the universe forces us to merge these two ideas into a single continuum. Distance and time become fundamentally inseparable because of one unyielding reality. The speed of light is not infinite. Light travels through a vacuum at a constant speed of approximately 186,000 miles per second. That seems instantaneous to us on Earth, where a signal can circle the entire globe in a fraction of a second. But space is unimaginably vast, and across these immense cosmic gulfs, light moves with a noticeable delay. When you look at the sun, you are not seeing it as it exists in this exact second. You are seeing light that left its surface 8 minutes and 20 seconds ago. If the sun were to suddenly disappear right now, Earth would remain bathed in its light and held in its gravitational embrace for more than 8 minutes before anyone noticed a thing. When you look at the planet Jupiter, you are seeing it as it was up to 45 minutes in the past. When you look at the nearest star system, Alpha Centauri, you are looking 4.3 years back in time. This means that every telescope, every camera, and even your own eyes are time machines. We never observe the universe as a present state, we observe a layered history. The deeper into space we peer, the further back in time we travel. This fundamental link between distance and time sets up a natural limit. Since modern physics indicates that the universe began roughly 13.8 billion years ago during the Big Bang, light has only had 13.8 billion years to travel through space. At first thought, it seems logical to assume that the absolute edge of what we can see must be 13.8 billion light-years away in any direction. If the universe is 13.8 billion years old, then light could only have travelled 13.8 billion light-years to reach us. But the reality of space is far stranger and much more dynamic. Space itself is not a static backdrop where galaxies simply drift around. Space is continuously stretching and expanding. While the light from the most ancient cosmic sources was travelling toward us over those 13.8 billion years, the space between those sources and Earth was expanding. The physical locations that emitted that ancient light have been carried much further away from us by the expansion of the fabric of space itself. When cosmologists calculate this expansion using established mathematical models, they find that the objects that emitted the earliest light we can detect are no longer 13.8 billion light-years away. Today, those distant points are estimated to be roughly 46.5 billion light-years from Earth. This creates a spherical boundary centered precisely on us, a sphere with a radius of 46.5 billion light-years and a total diameter of roughly 93 billion light-years. This immense volume of space is what scientists call the observable universe. It encompasses every star, every galaxy, every particle, and every photon whose light or signal has had enough time to reach Earth since the beginning of time. Everything inside this cosmic sphere is, in principle, theoretically accessible to our instruments. However, the existence of this boundary leads directly to one of the most profound questions in all of science. What lies beyond the 46.5 billion light-year line? The short answer is that we simply do not know with absolute certainty. By definition, any region of space beyond this cosmic horizon is fundamentally invisible to us today because its light has not had enough time to reach our detectors. But based on our current understanding of physics, scientists have developed several strong hypotheses. First, there is no physical reason to believe that space simply ends at 46.5 billion light-years. There is no physical wall, no edge, and no sudden drop-off into nothingness. If you were magically transported to an observer sitting right at the edge of our observable bubble, 46.5 billion light-years away, their view of the cosmos would likely look very similar to ours. They would sit at the center of their own observable bubble of 46.5 billion light-years in radius, overlapping with ours, filled with galaxies, stars, and cosmic structures. To them, Earth would be sitting on the outer edge of their observable horizon. Mainstream cosmological models suggest that the entire unobserved universe is vastly larger than the small slice we can measure. Some mathematical models based on cosmic inflation, a brief period of ultra-rapid expansion in the earliest moments of the universe, suggest that the entire universe could be at least 10 to the power of 23 times larger than our observable bubble. Other theoretical frameworks suggest that the universe may be spatially infinite, stretching endlessly in all directions with an endless distribution of matter. Yet, we must remain scientifically cautious. Because we cannot receive signals from beyond our horizon, we cannot definitively prove whether the universe outside our bubble is truly infinite, whether it curves back on itself in a giant closed shape, or whether physical laws operate slightly differently in regions far beyond our view. The unobserved universe remains one of the greatest mysteries in modern science, an infinite ocean of possibilities hidden just beyond the reach of our light. Long before humanity possessed orbiting space telescopes, giant ground-based reflectors, or sophisticated electronic sensors, our ancestors looked up at the night sky using only the raw biological tools provided by nature, the human eye. For thousands of years, this biological organ was our sole window into the expanse of the cosmos. To early stargazers, the blanket of stars visible on a dark night felt completely overwhelming, appearing like an infinite collection of suns scattered across the void. However, when we analyze human sight through a strict scientific lens, the reality of what our eyes can actually perceive is astonishingly limited. To understand why human vision is so constrained in space, we must look at how the human eye functions as an optical instrument. Our eyes are essentially biological cameras, but they possess tiny apertures and very short exposure times. The pupil of a fully dark-adapted human eye expands to a maximum diameter of only about 7 millimeters. This tiny opening determines how many light particles, or photons, can enter the eye at any given moment. Furthermore, unlike a camera that can accumulate light over minutes or hours to reveal faint details, the human brain processes visual information in real time, refreshing the image roughly every fraction of a second. As a result, if a distant celestial object does not send a sufficient concentration of photons into that tiny 7 millimeter opening within a fraction of a second, the light receptors in our retina simply will not trigger a signal to the brain. The object remains completely invisible to us. Because of these biological constraints, human vision can only register stars down to a certain threshold of brightness, known in astronomy as the sixth apparent magnitude. On a pristine, perfectly clear night, away from all light pollution, humidity, and atmospheric turbulence, the human eye can see only a tiny fraction of the stars in our galaxy. While people often imagine they are seeing millions of stars when looking at a dark sky, careful astronomical counting reveals that across the entire celestial sphere surrounding Earth, Only about 9,000 stars are bright enough to be seen by human eyes. Because half of the sky is always blocked by the earth beneath your feet, and because atmospheric haze near the horizon obscures faint objects, an observer standing in the darkest spot on Earth at any single moment can see, at most, roughly 2,500 to 4,500 individual stars. Every single one of those individual stars belongs to our own home galaxy, the Milky Way. More strikingly, the vast majority of those visible stars are our immediate stellar neighbours, located within a tiny local neighbourhood of a few hundred to a few thousand light-years from Earth. Beyond that modest distance, individual stars become far too faint for our biological lenses to resolve. This brings us to a remarkable question. What is the absolute furthest object a human being can see without the assistance of any optical technology whatsoever? The answer lies far beyond the stars of our local neighbourhood. Under exceptional sky conditions, an observer with sharp vision can spot a faint, hazy smudge of light in the constellation Andromeda. That tiny, ghostly cloud is not a star, a nebula, or a cloud of dust inside our galaxy. It is the Andromeda Galaxy, an entirely separate island universe containing roughly 1 trillion stars, located approximately 2.5 million light-years from Earth. When you look at Andromeda with your bare eyes, the light striking your retina left that galaxy 2.5 million years ago, long before modern human beings walked the surface of Earth. The reason we can see Andromeda, despite its staggering distance, is sheer power in numbers. While an individual star at that distance would be far too dim to detect, the combined light of hundreds of billions of stars blending together provides just enough photons to register as a subtle, faint blur on the human retina. Under extremely rare and ideal conditions, some highly experienced observers claim to barely glimpse the Triangulum galaxy, which lies roughly nearly 3 million light-years away, but it sits right at the absolute physical threshold of unassisted human perception. When we step back and evaluate these biological facts, the true scope of what our ancestors saw becomes startlingly clear. Throughout 99% of human history, humanity lived under the impression that they were gazing upon the entirety of creation. In truth, every single star visible to the naked eye, along with the faint glow of the Milky Way band overhead, represented nothing more than a microscopic speck within our own galaxy, supplemented by a tiny handful of hazy neighbouring galaxies. Our biological eyes give us a deeply deceptive view of the cosmos. They show us a dark sky lightly dusted with stars, creating the impression of a quiet, mostly empty neighbourhood. In reality, the human eye is blind to 99.999% of the matter, energy and structures that fill the observable universe. We were trapped in a tiny biological room, looking out through a pinhole. To see what lay beyond our immediate backyard, humanity had to invent new tools that could artificially enlarge our eyes and capture the light that had been falling silently on Earth for billions of years without ever being seen. For thousands of years, the strict biological limitations of the human retina remained an unbreakable barrier. Human understanding of the universe was essentially capped by what a 7mm pupil could gather in a fraction of a second. But in the early 17th century, a dramatic leap forward fundamentally shattered this boundary, transforming our relationship with the night sky forever. The invention and refinement of the telescope did not merely enhance human sight, it effectively magnified the light-gathering area of the human eye by orders of magnitude, kicking off a centuries-long technological evolution that would eventually push our vision to the edge of the cosmic horizon. The revolution began humbly when early pioneers like Galileo Galilei aimed primitive glass lenses toward the heavens. Galileo's first telescope had an aperture of just a few centimeters and crude optics, yet it immediately revealed phenomena that had remained invisible since the dawn of humanity. Moons were seen orbiting Jupiter, cratered landscapes were mapped on our moon, and the hazy white band of the Milky Way resolved into millions of previously hidden individual stars. From a physics perspective, the fundamental breakthrough of the optical telescope was remarkably simple. It acted as a massive bucket for collecting light particles. By focusing photons from a large physical area into a tiny beam that could enter a human pupil, These instruments allowed astronomers to see objects far dimmer and more distant than nature ever intended. Over the next 3 centuries, optical technology evolved at a breathtaking pace. Astronomers quickly realized that glass lenses faced severe physical limits due to weight, manufacturing flaws, and chromatic distortion. This led to the development of reflecting telescopes, which used curved glass mirrors coated with reflective metal to gather and focus light. Mirror sizes grew steadily from a few inches across to massive structures spanning feet, then yards. By the early 20th century, instruments like the 100-inch Hooker telescope at Mount Wilson Observatory in California allowed Edwin Hubble to make 2 world-shattering discoveries. First, that faint, fuzzy nebulae were actually entire independent galaxies far outside our own, and second, that these galaxies were rushing away from each other in an expanding universe. However, as ground-based optical telescopes grew larger and more sophisticated, they slammed directly into a new environmental wall: Earth's atmosphere. The blanket of air that protects life on Earth is a nightmare for precision astronomy. Atmospheric turbulence bends, scatters and distorts incoming light rays, the very effect that causes stars to twinkle, placing a hard ceiling on how sharply a ground-based telescope can resolve distant celestial details. Furthermore, water vapor, ozone, and other atmospheric gases absorb and block large portions of the electromagnetic spectrum, completely blinding ground observers to vast swathes of cosmic information. To escape this atmospheric veil, humanity took a monumental leap in 1990 by launching the Hubble Space Telescope into low Earth orbit. Sitting roughly 340 miles above the turbulent atmosphere, Hubble's 2.4-meter primary mirror possessed a crystal-clear view of the deep universe. Free from atmospheric blurring, Hubble could perform long-exposure observations, staring at single tiny patches of the sky for hours, days, or even weeks at a time, continuously accumulating faint photons on electronic sensors. The ultimate demonstration of this technological capability occurred in late 1995, when astronomers decided to conduct a risky and unprecedented experiment. They pointed Hubble at an apparently empty, dark patch of sky near the Big Dipper, a spot so tiny it was equivalent to looking at a grain of sand held at arm's length, a region where ground telescopes saw almost nothing. For 10 consecutive days, Hubble pointed at this pitch-black void, collecting whatever scattered photons managed to arrive. The resulting image, known as the Hubble Deep Field, stunned the world and revolutionized cosmology. The seemingly empty, dark void was not empty at all. It was teeming with nearly 3,000 distant, previously undiscovered galaxies, each containing tens or hundreds of billions of stars, shining across vast stretches of space and time. Subsequent, even deeper observations, such as the Hubble Ultra Deep Field and Extreme Deep Field, revealed thousands more galaxies stacked in a narrow tunnel stretching back over 13 billion years into the past. These images prove that no matter where we look in the night sky, even in the darkest spots, space is densely populated with galaxy structures. Yet, despite the astonishing success of optical telescopes like Hubble, astronomers eventually ran into a fundamental boundary dictated by the laws of physics and the dynamic geometry of the universe: the limitations of visible light itself. Visible light, the narrow rainbow of colors that human eyes evolved to detect, represents only a tiny fraction of all electromagnetic radiation. As optical telescopes tried to peer deeper and deeper into the early universe, they encountered a phenomenon known as cosmological redshift. This effect is a direct consequence of the expansion of space. When light emitted by a distant galaxy travels across billions of light-years of space to reach us, it does not travel through a static void. The fabric of space itself is expanding while the light wave is in transit. As space stretches, the wavelength of the traveling light gets physically stretched along with it. Light that was originally emitted as short, high-energy visible light, or even ultraviolet radiation, gradually has its wavelengths pulled long and flat over billions of years of travel. By the time that light finally reaches our neighborhood of space, after traveling for more than 13 billion years, its wavelength has been shifted completely out of the visible spectrum and pushed deep into the longer, invisible wavelengths of infrared radiation. This cosmological redshift creates a hard wall for optical light astronomy. Beyond a certain distance and age in cosmic history, even the most powerful optical telescope in the world is functionally blind. The light from the very first stars and galaxies that formed after the Big Bang has been stretched so far by the expanding universe that it simply no longer exists in the visible light spectrum when it reaches our detectors. To look further back into the primordial dawn of the cosmos and map the true extent of our observable bubble, astronomers realized they could no longer rely on visible light alone. To see the hidden universe, we had to build an entirely new generation of instruments, telescopes engineered to perceive an invisible reality through light that human eyes could never hope to see. To push past the optical boundary created by cosmological redshift and interstellar dust, astronomy underwent a radical transformation. Scientists realized that if we wanted to peer into the deepest corners of space and look back toward the beginning of time, we had to abandon our reliance on human visible wavelengths and embrace the invisible universe. Among the most crucial tools in this new era are infrared light and radio waves, two distinct regimes of the electromagnetic spectrum that reveal structures completely hidden from traditional optical telescopes. Infrared radiation occupies wavelengths just longer than the visible red light our eyes can process. In the cosmos, infrared light possesses two incredible advantages. First, as light travels across billions of light-years of expanding space, cosmological redshift stretches short ultraviolet and visible light rays straight into the infrared band. Second, infrared light has the unique physical ability to pass almost unimpeded through dense clouds of cosmic dust and interstellar gas. In optical light, regions like stellar nurseries or the dense centers of galaxies appear as pitch-black, impenetrable voids because thick soot-like dust particles scatter and absorb visible light. However, longer infrared wavelengths slide right through these dust grains. Where an optical telescope sees only an opaque dark wall, an infrared observatory sees straight through the veil, revealing newly born stars igniting inside dark nebulae, hidden planetary systems forming in circumstellar disks, and the glowing hearts of distant galactic collisions. The absolute pinnacle of infrared astronomy is the James Webb Space Telescope. Positioned nearly 1 million miles from Earth at the second Lagrange point, Webb was specifically designed to capture faint, ancient infrared light that has been traveling across the cosmos for over 13 billion years. Equipped with a primary mirror spanning over 21 feet and shielded by a massive tennis court-sized sunshield to keep its instruments near absolute zero, Webb can detect infrared photons emitted by the very first generations of stars and galaxies that assembled after the Big Bang. By peering through cosmic dust and gathering deeply redshifted infrared light, Webb has pushed our visual boundary further than ever before. It has revealed fully formed, complex galaxies that existed just a few 100 million years after the birth of the universe, challenging previous theoretical models of early galactic evolution and opening an entirely new window onto cosmic history. However, infrared light is not the limit of our reach. If we extend our vision even further down the spectrum to much longer wavelengths, we enter the domain of radio astronomy. Radio waves range from a few millimeters to miles in length, allowing us to observe an entirely different set of cosmic phenomena, most notably the oldest light in existence, the cosmic microwave background. To understand what the cosmic microwave background represents, we must look back to the state of the early universe. Roughly 13.8 billion years ago, immediately following the Big Bang, the universe was extremely hot, dense, and opaque. It was a churning plasma soup of free protons, electrons, and high-energy light particles. Photons could not travel freely because they were constantly colliding with free electrons, trapped in a chaotic cosmic fog. This opaque state persisted for approximately 380,000 years. As the universe expanded, it gradually cooled. Eventually, the temperature dropped to roughly 3,000 degrees Kelvin, allowing free electrons and protons to combine for the first time to form neutral hydrogen atoms. With the free electrons suddenly bound into atoms, space became instantly transparent. Photons were suddenly set free to travel unimpeded across the void in every direction. This event is known as recombination, or the moment of cosmic decoupling. That ancient flash of light, released 380,000 years after the Big Bang, has been traveling through space ever since. Over 13.8 billion years, the relentless expansion of space has stretched those original high-energy photons by a factor of roughly 1100. What began as intense, blinding ultraviolet and visible radiation has been stretched out into low-energy microwave and radio wavelengths. When radio astronomers detected this pervasive signal for the first time in the mid-1960s, they discovered a nearly uniform glow arriving from every single direction in the night sky. This thermal residue is the cosmic microwave background, the oldest observable light in the universe. It acts as a literal snapshot of the universe when it was just a tiny fraction of its current age, long before any stars, planets, or galaxies had formed. The cosmic microwave background represents an absolute observational wall for light-based astronomy. Because the universe prior to 380,000 years after the Big Bang was an opaque plasma fog, no free light exists from the first 380,000 years of cosmic time. No optical, infrared, or radio telescope, no matter how large or advanced, will ever be able to directly capture light from before that epoch. Through infrared space observatories like Webb and radio mapping of the cosmic microwave background, astronomers have succeeded in extending our observational coverage across vast expanses of space and time. Infrared light allows us to look through dusty shrouds and capture the first embryonic galaxies, while radio waves allow us to map the very edge of the light-emitting cosmos. Together, these invisible wavelengths have transformed our understanding from a local, optical view into a deep, multispectral map of cosmic evolution. While infrared light and radio waves allow us to map the cool, distant, and ancient realms of the cosmos, the opposite end of the electromagnetic spectrum reveals a wildly different universe, one of extreme violence, unimaginable temperatures, and catastrophic gravity. This high-energy domain is governed by X-rays and gamma rays, the shortest and most energetic wavelengths of light in existence. To human eyes, the vast majority of deep space appears silent, dark, and tranquil. But when specialized space-based observatories look at the universe through high-energy radiation, that tranquil picture is replaced by a landscape of cosmic turbulence. X-rays are produced in environments where matter is heated to millions of degrees, such as the regions immediately surrounding black holes. A black hole itself emits no light from inside its event horizon, making it completely invisible to direct observation. However, when a supermassive black hole at the center of a galaxy feeds on surrounding gas and dust, that matter is drawn inward by extreme gravitational forces. As the material accelerates toward the speed of light and spirals into an accretion disk, friction and magnetic forces heat the gas to tens of millions of degrees. At these incomprehensible temperatures, the superheated material glows brilliantly in the X-ray spectrum before plunging past the point of no return. Space telescopes like the Chandra X-ray Observatory allow astrophysicists to trace these intense, energetic emissions, effectively mapping the immediate boundaries of black holes, detecting the powerful shock waves of exploded stars, and observing the vast, multi-million-degree reservoirs of gas that fill the voids between galaxy clusters. Pushed even further past X-rays lies the most energetic radiation of all, gamma rays. These cosmic rays are generated by the most violent cataclysms the universe can produce, such as the collapse of massive stellar cores into neutron stars, the collisions of binary neutron star pairs, or the birth cries of newly formed black holes. Gamma-ray bursts release more energy in a matter of a few seconds than our Sun will emit over its entire 10 billion-year lifetime. Instruments like the Fermi Gamma-ray Space Telescope scan the entire sky, capturing these fleeting, high-energy explosions from across billions of light-years. Through gamma-ray astronomy, we can observe real-time nuclear reactions in the hearts of exploding supernovae and trace the most powerful particle accelerators in the cosmos, known as blazars, supermassive black holes shooting relativistic jets of plasma directly toward Earth. When we combine radio waves, microwaves, infrared light, visible light, ultraviolet rays, X-rays, and gamma rays, we are looking at the full electromagnetic spectrum. Understanding the true scope of this spectrum delivers a profound realization about how narrow our biological window truly is. Consider an analogy to appreciate just how tiny visible light really is compared to the entire spectrum. Imagine taking the complete electromagnetic spectrum, from the longest low-frequency radio waves measuring miles across, all the way to the shortest, ultra-dense gamma-ray waves, and stretching it out like a continuous ribbon of tape across the entire continental United States, spanning roughly 3,000 miles from Los Angeles to New York City. Along that 3,000-mile strip of information, the narrow band of visible light, every shade of red, orange, yellow, green, blue and violet that the human eye evolved to see, would occupy a stretch smaller than the width of a single human hair. Think about what that comparison means. Throughout 99.9% of human existence, humanity believed it was seeing the vast majority of reality simply by looking up on a clear night. In truth, our eyes were tuned to a microscopic fraction of the energetic symphony occurring in space. By building spaceborne sensors capable of converting invisible radio waves into maps, infrared heat into detailed structural images, and high-energy X-rays and gamma rays into dynamic data streams, modern science has effectively gifted humanity a new set of artificial senses. We are no longer limited to the sliver of reality granted by our biological eyes. We have unlocked the rest of the 3,000-mile tape, turning the seemingly silent, pitch-black void into a multi-wavelength tapestry of cosmic activity. Yet, even with every band of the electromagnetic spectrum completely unlocked, another sobering limit remains. Everything we have discussed so far, from radio waves to gamma rays, relies fundamentally on light. What happens when the cosmos produces events and structures that emit no light at all? To observe those completely hidden phenomena, scientists had to look beyond light entirely and pioneer methods to literally feel the fabric of space itself. For hundreds of years, humanity operated under the assumption that observing the universe was entirely synonymous with capturing electromagnetic radiation. Whether using Galileo's early glass lenses, the giant mirrors of space observatories, or sprawling radio dish arrays, every single instrument we built relied on the exact same fundamental messenger, the photon. But light, for all its speed and versatility, has severe physical vulnerabilities. Photons can be absorbed by dense clouds of interstellar soot, scattered by ionized gas, delayed by gravitational fields, or blocked entirely by opaque environments. Furthermore, some of the most violent and enigmatic events in the cosmos generate almost no light at all. To break through this barrier, astrophysicists in the 21st century developed entirely new ways to perceive the cosmos without using light. Instead of looking at photons, we have learned how to capture elusive subatomic ghost particles and physically measure the microscopic vibrations of spacetime itself. The first of these revolutionary non-optical messengers is the neutrino. Neutrinos are fundamental subatomic particles that possess almost zero mass, no electrical charge, and interact with other forms of matter almost exclusively through the extremely weak subatomic force. Because they have no charge and virtually no mass, neutrinos do not feel electromagnetic forces. They pass through solid objects as if they were entirely empty space. To understand just how phantom-like neutrinos are, consider this. Right now, approximately 100 trillion neutrinos are passing straight through every single square inch of your body every second, streaming outward from nuclear fusion reactions deep inside the core of our Sun. They pass through your body, travel down through the entire diameter of the solid Earth, and emerge out the other side without colliding with a single atomic nucleus along the way. While this ghostly nature makes neutrinos nightmarishly difficult to catch, it also makes them the most pristine cosmic messengers imaginable. Unlike light, which gets trapped and scattered inside the dense, fiery interiors of exploding stars or the chaotic swirling disks around supermassive black holes, neutrinos escape instantaneously. They travel in perfectly straight lines across billions of light-years of space, completely unaffected by cosmic dust clouds, gas fields, or magnetic barriers. To intercept these particles, scientists had to construct detectors on a scale never before attempted. The most famous of these is the Ice Cube Neutrino Observatory, built deep beneath the ice cap at the South Pole. Engineers drilled 86 boreholes over 1.5 miles deep into the pristine Antarctic ice sheet, lowering strings of thousands of ultra-sensitive optical sensors into a solid cubic kilometre of transparent ice. On extremely rare occasions, a high-energy neutrino travelling from a distant cosmic event crashes directly into the nucleus of a water molecule inside the ice. This ultra-rare collision produces a cascade of charged secondary particles that travel through the ice faster than light can travel through that same medium, generating a faint, cone-shaped flash of blue glow known as Cherenkov radiation. By precisely measuring the arrival time and angle of this blue flash across thousands of sensors, scientists can calculate the energy of the neutrino and trace its straight flight path back to its distant birthplace across the universe. Through neutrino observatories, we have begun peering directly into the fiery hearts of extreme active galaxies and supermassive black hole jets that remain completely opaque to traditional light telescopes. Yet, as extraordinary as neutrino astronomy is, the second non-light observational method represents an even more radical conceptual leap, measuring gravitational waves. In 1915, Albert Einstein published his theory of general relativity, introducing the concept that space and time are not a static background, but an active, flexible, four-dimensional fabric known as spacetime. Einstein's mathematical equations predicted that whenever massive celestial objects accelerate violently, such as two black holes orbiting each other at near-light speed, they should churn and warp the spacetime around them, sending ripples of pure gravitational energy radiating outward across the universe at the speed of light. For a full century, gravitational waves remained purely theoretical, because gravitational forces are extraordinarily weak compared to other fundamental forces. Einstein himself believed that the distortion caused by these ripples would be so infinitely small that human technology would never possess the precision required to detect them. That theoretical impasse shattered in September of 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of gravitational waves in human history. LIGO operates two massive facilities located thousands of miles apart in Washington State and Louisiana. Each facility consists of two perpendicular vacuum pipes stretching nearly 2.5 miles in length. Powerful laser beams are split and sent down both arms, bouncing off suspended mirrors before recombining at a central detector. When a gravitational wave passes through Earth, it physically stretches space-time in one direction, while compressing it in the perpendicular direction, altering the physical length of LIGO's vacuum arms by a microscopic fraction. The scale of precision required for this measurement is almost beyond comprehension. To detect a passing gravitational wave, LIGO's instruments must measure a change in distance smaller than 1/10,000th of the diameter of a single proton over a 2.5-mile path. The first signal detected by LIGO, catalogued as GW150914, was generated by the catastrophic collision of two stellar mass black holes roughly 1.3 billion light-years away. In the final fraction of a second before they merged, these two cosmic titans converted an amount of mass equivalent to 3 times the entire mass of our Sun directly into pure gravitational energy, radiating more power than the light of every star in the entire observable universe combined. Yet, because black holes do not emit light, this immense cosmic event was completely invisible to every optical, radio, and X-ray telescope on Earth. We did not see the collision with light. We felt the physical fabric of our planet shudder as the ripples rolled past. The emergence of neutrino detectors and gravitational wave interferometers marks the dawn of what scientists call multi-messenger astronomy. Instead of relying exclusively on the single sense of sight, humanity has effectively developed the cosmic equivalents of hearing and touch. In 2017, when two ultra-dense neutron stars collided, astronomers detected the event simultaneously through gravitational waves, gamma rays, X-rays, visible light, and radio signals, piecing together a comprehensive, multi-layered picture of a single cosmic cataclysm. Nevertheless, we must remain grounded in scientific reality. Multi-messenger astronomy is still in its infancy. Our current detectors can only capture the loudest, most extreme gravitational crashes and the most energetic neutrino bursts within a relatively localized slice of cosmic space. Countless subtler vibrations, low-frequency gravitational hums from supermassive black hole binaries, and background neutrino signals from the earliest seconds of the Big Bang remain just beyond the threshold of our modern sensitivity. We have proven that the universe speaks in languages other than light, but we are only just beginning to decipher the first few words of that non-electromagnetic dialogue. Even with our most sophisticated space telescopes, ultra-sensitive radio arrays, neutrino detectors and gravitational wave interferometers, humanity still faces immense physical blind spots that severely limit our view of the cosmos. These barriers are not merely technological. Some are structural obstacles built right into our local celestial environment, while others stem from the elusive, unseen components that appear to make up the vast majority of the universe itself. The first major physical blind spot is an ironic consequence of our own cosmic address. We live inside the disk of the Milky Way galaxy, a massive spiral structure spanning over 100,000 light-years across, densely packed with hundreds of billions of stars, vast molecular clouds, and thick lanes of carbon and silicate dust. Because our solar system sits roughly halfway out from the galactic center within this flattened disk, looking out into deep space means our line of sight in certain directions is directly obstructed by our own galaxy's dense stellar core and thick dust clouds. In observational astronomy, this block strip of the sky is formally known as the zone of avoidance. This region covers roughly 20% of the entire night sky, a massive, continuous blind swath where optical light from distant galaxies is almost completely absorbed and scattered by the interstellar dust of the Milky Way. For centuries, astronomers could only guess what lay behind this galactic wall. In recent decades, scientists have used long-wavelength radio waves, infrared instruments, and X-ray observatories to partially pierce through this thick shroud. These efforts revealed previously hidden superclusters of galaxies, along with a mysterious gravitational anomaly known as the Great Attractor, a massive concentration of mass pulling our galaxy and thousands of others toward it at hundreds of miles per second. Yet, even with our modern non-optical tools, our mapping of the zone of avoidance remains incomplete, leaving a substantial slice of the local universe shrouded in relative obscurity. However, a far more profound and humbling blind spot is not a matter of physical dust blocking our vision. It is the realization that the overwhelming majority of the universe's total mass and energy is fundamentally invisible, undetectable by any form of electromagnetic radiation we can produce or capture. This invisible reality is divided into two major theoretical components: dark matter and dark energy. To maintain strict scientific accuracy, we must emphasize that dark matter and dark energy are not objects we have physically captured or directly observed in a laboratory. Rather, they are leading theoretical frameworks and mathematical models developed to explain consistent, unexplained gravitational phenomena observed throughout the cosmos. The hypothesis of dark matter arose when astronomers began measuring the rotational speeds of spiral galaxies. According to the standard laws of Newtonian gravity and general relativity, the stars at the outer visible edges of a spinning galaxy should rotate much slower than the stars near the dense center, just as the outer planets in our solar system orbit the Sun much slower than the inner planets. But in the 1970s, careful measurements demonstrated that the outer stars in galaxies were moving just as fast as the inner stars. Based on the amount of visible matter, such as stars, gas, and dust, the outer regions of these galaxies were moving so fast that the galaxies should have flown completely apart. To reconcile this discrepancy within our established understanding of gravity, astrophysicists propose that galaxies are embedded within massive, invisible spherical halos of an unknown substance termed dark matter. This hypothetical matter interacts gravitationally with normal baryonic matter, providing the extra gravitational glue needed to hold spinning galaxies together and keep large galaxy clusters from dispersing. Further indirect evidence for this model comes from gravitational lensing, a phenomenon where the mass of an unseen cluster bends and distorts the light traveling from more distant galaxies behind it. By measuring how much the light is bent, astronomers can map the total mass distribution of the lensing cluster, consistently finding far more mass than can be accounted for by visible matter alone. Yet, despite extensive worldwide searches using deep underground cryogenic detectors, particle accelerators, and sensitive space telescopes, not a single particle of dark matter has been directly detected or confirmed. While popular candidate theories suggest weakly interacting massive particles, sterile neutrinos, or hypothetical particles called axions, alternative hypotheses, such as modified theories of gravity that alter the mathematical laws of physics at large scales, continue to be explored. Until direct physical detection occurs, dark matter remains an inference based on gravitational effects rather than an observed substance. If dark matter represents an enormous gravitational mystery, dark energy presents an even deeper cosmological puzzle. In the late 1990s, two independent teams of astronomers measured the distances and redshift speeds of distant exploding white dwarf stars, known as Type 1a supernovae. Because these supernovae have a remarkably consistent intrinsic brightness, they act as cosmic standard candles, allowing scientists to measure precise distances across billions of light years. The astronomers expected to find that the expansion of the universe was slowing down over time, pulled inward by the collective gravity of all the matter in space. Instead, the data revealed the exact opposite. The expansion rate of the universe has been accelerating over the past 5 to 6 billion years. To account for this cosmic acceleration within the framework of general relativity, cosmologists introduced the concept of dark energy, a smooth, repulsive property of empty space or an unknown energy field that exerts negative pressure, driving space to stretch apart at an ever-increasing rate. The simplest mathematical formulation treats dark energy as a cosmological constant, an inherent, unchanging energy density woven into the vacuum of space itself. Other dynamic hypotheses suggest an evolving scalar energy field known as quintessence. Just like dark matter, dark energy has never been directly observed, isolated, or explained at a fundamental physical level. We observe its large-scale effects on cosmic expansion, but its underlying nature remains completely unknown. When scientists combine the latest measurements from cosmic microwave background surveys, large-scale galaxy distribution maps, and supernova observations, they arrive at the standard cosmological model known as the lambda cold dark matter model. This model presents a staggering inventory of the universe's total mass energy content. According to these calculations, ordinary baryonic matter, everything made of atoms, including every star, planet, gas cloud, tree, ocean, animal, and human being, along with all the light and neutrinos in existence, accounts for only roughly 5% of the total mass energy of the universe. The remaining 95% is composed entirely of the invisible dark sector. Approximately 27% is attributed to cold dark matter, and approximately 68% is attributed to dark energy. This cosmological calculation delivers an incredible reality check. When we look out into the cosmos with our most powerful optical, radio, infrared, and X-ray telescopes, we are not looking at the vast majority of what exists. We are merely observing the luminous foam resting atop an immense, dark, and unmapped cosmic ocean. 95% of the physical ingredients that dictate the structure, evolution, and ultimate fate of our universe remain entirely unobserved by direct physical means, standing as the greatest unanswered questions in all of modern science. When we assemble all the pieces of modern observational astrophysics, we arrive at a startling, deeply humbling calculation. We often look at spectacular images produced by modern space observatories and feel a sense of triumphant mastery, believing that humanity has successfully charted the cosmos. But when we perform a rigorous scientific audit of what we have actually measured, recorded, and verified, the reality is far more modest. By almost every physical metric, humanity has directly observed only a vanishingly small fraction of the universe. Let us first examine the universe through the lens of mass and energy. As established by modern cosmological surveys, the standard model indicates that roughly 95% of the total mass energy content of the universe resides in the dark sector, dark matter, and dark energy. Neither of these components has ever been directly observed, isolated, or physically measured in a laboratory. They are inferred entirely from their large-scale gravitational and cosmological effects. That means right from the start, 95% of the cosmos is completely beyond our direct physical gaze. This leaves the remaining 5%, ordinary baryonic matter. This is the tangible material that forms everything we have ever touched, seen, or interacted with, including every atom of hydrogen, carbon, and iron in existence. One might naturally assume that we have at least observed the vast majority of this 5%. After all, the night sky is filled with billions of shining stars, glowing emission nebulae, and brilliant galaxies. However, astrophysical surveys reveal that luminous stars, planets, and glowing clouds of gas do not make up the bulk of ordinary matter. In fact, all the stars in all the galaxies in the observable universe combined account for only about 6 to 7% of that 5%. Planets, asteroids, and living organisms make up an amount so tiny it barely registers as a rounding error. Where is the rest of the normal matter? Most of the baryonic material in the cosmos, roughly 80 to 90% of it, exists as extremely diffuse, invisible clouds of ionized hydrogen and helium gas drifting in the vast, dark spaces between galaxies. This tenuous material, often referred to as the warm-hot intergalactic medium, is so spread out that a cubic meter of intergalactic space might contain only a single atom. Because this gas is so incredibly thin and rarely collides with other particles to emit light, it is exceptionally difficult to detect directly. Astronomers can only trace its presence indirectly by observing how the light from extremely distant, ultra-bright quasars is subtly absorbed as it passes through these invisible intergalactic gas filaments. When you add up the numbers, all the visible glowing matter that we can easily point our optical telescopes at represents less than 0.1% of the entire mass-energy content of the universe. The situation becomes even more striking when we consider the total number of galaxies within our observable bubble. Based on deep field observations and mathematical models of galaxy formation, cosmologists estimate that the observable universe contains somewhere between 100 billion and 2 trillion galaxies. It is crucial to understand that scientists have not individually located, catalogued, or photographed 1 to 2 trillion galaxies. That staggering number is a statistical extrapolation. To arrive at this figure, astronomers point instruments like the Hubble Space Telescope or the James Webb Space Telescope at an exceptionally tiny, seemingly empty patch of the dark sky for hundreds of hours. They count every faint smear of light in that microscopic visual cone, calculate the volume of space surveyed within that narrow beam, and then multiply that number across the entire spherical surface of the night sky. This extrapolation relies on a foundational concept in cosmology, known as the cosmological principle. This principle posits that on sufficiently large scales, distances spanning hundreds of millions of light years, the universe is both homogeneous and isotropic. In simple terms, it assumes that the universe has roughly the same density and structural properties everywhere, and looks essentially the same in every direction. While the cosmological principle is strongly supported by the uniform temperature of the cosmic microwave background, it remains an overarching scientific assumption. We infer that unmapped regions of space contain trillions of galaxies because the tiny pinholes we have sampled are crowded with them. In actual practice, how many individual galaxies have human instruments truly catalogued? Through large-scale automated astronomical surveys such as the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, humanity has mapped the precise positions and light spectra of several million galaxies. A few million galaxies is an astonishing technological achievement, but when compared to an estimated total of 2 trillion, it represents only a fraction of a single percent of all the galaxies that theoretically inhabit our observable sphere. Over 99% of the galaxies in our own observable universe remain unvisited by human data collection, existing only as statistical points in our cosmological models. Furthermore, for the overwhelming majority of galaxies we have catalogued, our observation is limited to a handful of blurred pixels or a faint spectral line. We do not possess detailed maps of their internal stellar populations, we cannot resolve their individual star clusters, and we cannot see their planets. We simply register that a faint source of electromagnetic energy exists at a particular coordinate in the past. When we combine the physical composition of space with the limits of our mapping programs, the honest conclusion is undeniable. we live inside an observable sphere 93 billion light-years across. Within that sphere, 95% of the contents are made of invisible, mysterious phenomena we cannot directly see. Of the 5% that is visible matter, the vast majority is cold, diffuse gas floating in deep voids. And of the luminous galaxies that populate space, humanity has individually catalogued only a microscopic fraction. We have begun to read the opening sentence of the Cosmic Encyclopedia, but the rest of the library remains completely unexplored. As we look ahead to the coming decades, humanity is preparing to launch a new generation of observational instruments designed to push the boundaries of what is scientifically detectable. These upcoming observatories aim to expand our multi-messenger capabilities and map the dark corners of the observable bubble with unprecedented precision. Among the most anticipated future instruments is the Laser Interferometer Space Antenna, known as LISA. Unlike Earth-based gravitational wave detectors whose arms are limited to a few miles by local geography and seismic noise, LISA is planned as a constellation of 3 spacecraft, flying in a precision triangular formation millions of miles apart in deep space. By firing lasers across vast interplanetary distances, LISA will be sensitive to low-frequency gravitational waves, allowing astrophysicists to listen directly to the collisions of supermassive black holes at the centers of colliding galaxies and observe the gravitational hum of thousands of compact binary systems throughout our own Milky Way. On the ground, massive engineering endeavors such as the Square-Kilometre Array, a sprawling collection of thousands of radio antennas spread across Africa and Australia, will create the largest, most sensitive radio observatory in human history. This facility will be capable of mapping the distribution of neutral hydrogen gas throughout cosmic history, peering directly into the cosmic dawn when the very first stars ignited and cleared the primordial darkness. Yet, even as our observational tools reach levels of precision that were once purely theoretical, astronomers are faced with a profound, almost tragic cosmological realization. Our opportunity to observe the broader universe is strictly running on borrowed cosmic time. Based on our current standard cosmological model, the universe is not merely expanding, that expansion is accelerating under the continuous repulsive influence of dark energy. Because space itself can stretch without being constrained by the speed of light, the vast distances between distant galaxy clusters are growing wider every second. Over cosmological timescales, distant galaxies will be carried away from us at an effective velocity that exceeds the speed of light. This does not violate the laws of special relativity, because the galaxies themselves are not moving through local space faster than light. Rather, the fabric of space between us and those distant systems is stretching faster than their light can cross the expanding gap. As this acceleration continues over hundreds of billions of years, a process of cosmic isolation will inevitably unfold. One by one, distant galaxy clusters will cross past our cosmological event horizon. The light emitted by those far-off galaxies will never again be able to reach our region of space. Their images will gradually stretch to infinitely long wavelengths, becoming dimmer and redder until they fade into absolute, undetectable blackness. Eventually, our local gravitational group, consisting of the Milky Way, the Andromeda Galaxy, and a handful of small satellite dwarf galaxies, will merge together into a single, giant, unified elliptical galaxy. By that distant epoch, every other galaxy outside our immediate gravitationally bound island will have been pushed far beyond the observable horizon. If future intelligent civilizations emerge on planets orbiting the surviving stars in that distant era, their night sky will look entirely different from ours. When their astronomers build telescopes and scan the heavens, they will see only the stars of their own, single, combined galaxy surrounded by complete, impenetrable blackness. The cosmic microwave background would have been stretched to wavelengths so long and faint that it will be entirely undetectable against background thermal noise. Those future observers will find no observational evidence that the universe is expanding, no trace of a Big Bang, and no sign that billions of other galaxies ever existed across a vast, connected cosmos. They will look out into the void and naturally conclude that their single island galaxy is the entirety of physical reality, forever isolated in an empty, static ocean of space. This cosmological consequence adds an extraordinary sense of urgency and privilege to our current moment in time. Humanity happens to exist in a rare, golden cosmic window. We live during an era when the universe is old enough to have formed heavy elements, rocky planets, and conscious minds capable of building scientific instruments, yet still young enough that the echoes of the Big Bang and the light of trillions of distant galaxies remain clearly visible across the sky. We are witnessing the grand cosmic tapestry at the precise moment it can still be seen, mapped, and understood before the accelerating expansion of space pulls the curtain closed forever. In the grand perspective of the cosmos, what we have directly observed is barely a single grain of sand on an endless cosmic shore. 95% of the universe remains veiled in the mysteries of the dark sector, and countless galaxies sit beyond our present reach. Yet, there is profound triumph in our journey. A fragile species bound to a pale blue dot has learned to read the spectrum of ancient light, feel the subtle ripples of spacetime, and map 13.8 billion years of cosmic history. We may occupy a modest corner of existence, but our curiosity reaches across the stars. Thank you for joining us on this cosmic exploration. If you enjoyed this journey through the frontiers of science, feel free to like and subscribe to join us for future deep dives. Before you go, drop a comment down below to let us know where on Earth you are watching from and what time it is for you right now. Until next time, keep looking up.